Okay, I think it's about time to start. We have a little earlier to have a better discussion or whatever. So good morning, good afternoon, ladies and gentlemen. It's about time to start. So my name is Eunjae Park from Yonsei University in Korea, in Seoul, Korea. And I was told that we start 10 minutes late, so we are about to start now. So I'm really honored to be the chair of this invited session. So we have three speakers on scientific numerical analysis and scientific computation. So just tell you that we have 45 minutes for the talk, including discussion and questions. If you don't want to get any questions, you can have 45-minute talk. Okay, I'm kidding. Okay, so anyway, so 45 minutes for the talk and include discussion. Okay, so I'm really glad to introduce our first speaker, Annalisa Buffa from Italy. So she received her PhD in year 2000 in University of Milano in Italy from under the supervision of Franco Prece. And she has done very nice work in many different areas. And the most important one now for her awards, she received the Premio Scagliata and Premio Ghiglieri, I don't know, but anyway, so the important one is this one, ERC. This is European Research Council. This project, this is very competitive. Even though you're good, you're not, many times you miss it, but she's good enough to get this important project fund. So I think I better not take her time. So please join me to welcome Annalisa Buffa.
So thank you very much for the kind introduction. Maybe I can skip it.
Now it's on.
Okay, thank you. So thanks a lot for the kind introduction. And so my talk is about spline differential forms. And the name that you see here is the group in Pavia, and the work I will speak about as being developed mainly with Giancarlo Sangalli and Rafael Vasquez. So before getting into the core of my presentation, I want to give a framework for what I'm doing, and the framework comes from applications. So I will try to give an idea on the kind of applications we want to solve and in which framework we want to solve them. And I will have this as a motivation to show how splines can be used as a tool in numerical methods for PDEs. Then I will go to the core of my presentation, that is the definition of spline differential forms and spline complexes from low-order Whitney forms, and then I will enter into the mathematics of the spline complexes, studying commuting projectors, interpretation of degrees of freedom, the geometric structure, and I will also give some hint on how one can construct stable, discrete star-Hodge operators for spline complexes, and then I will draw conclusions. In my talk there will be no numerical experiments because I decided to concentrate more on the mathematical side, but at the end I will point to a review paper where you find a lot of numerical tests showing how good are the techniques we are proposing. So the framework, so I start with the introduction. The frameworks comes from applications. Which kind of applications we aim at? We aim at computing equations like the one that you see here. This is magnetostatics in bounded domain with the possibly heterogeneous media, but it can also be Stokes or Navier-Stokes equation in a bounded domain, and can be waveguides, so propagation of modes within heterogeneous waveguides, or elasticity that can be linear, as the one I show here, or non-linear, possibly in presence of contact. This is an unbounded domain. We are also interested in an unbounded domain, so the typical problem is, for example, acoustics, so the propagation of acoustic waves outside the scatterer can be acoustic or can also be electromagnetics, and I want to point out that in these type of problems, the computational domain is the exterior of a geometry, and the definition of the geometry itself is often very challenging. The one you see here is a metamaterial, for example. So what is the common the common structure of all these problems? The common mathematical feature is that these problems reveal a geometric structure which needs to be preserved at the discrete level in order to obtain spurious free discretizations. And this has been the topic of a lot of work in numerical analysis that today takes the name of finite element exterior calculus. And I want to mention here that this name was given by Doug Arnold, and a lot of activity around these concepts started after the plenary talk at the International Congress of Mathematicians by Doug. And there are a number of people who have been involved in the definition and in the development of these techniques. In fact, I would say that finite element exterior calculus includes and has a lot, well, not includes, it has a lot in common with many numerical techniques. Some of them were older than these names, some of them are newer, like virtual elements, for example. And in all these techniques, we see that sometimes we need to preserve a certain geometric structure, and that means that we need to fall a little bit into the framework of an exterior calculus. So the nice aspect of this theory is that it conjugates differential geometry, functional analysis, and numerical analysis. But now, let's try to get a more broad perspective. So we are thinking of designing a solver for partial differential equations, and I first asked myself, and why we do so? Well, the general motivation is that PD simulators are ubiquitous in science and engineering. I would say this is the standard sentence that we hear. And I would say that it is ubiquitous especially in the process of product design. What is this process? I have a very simplified flow chart. So the process in general is like that. So we start from a geometry that is designed by a computer-aided design system. We run a simulation of that geometry to understand, for example, how the structure is behaving. And then we possibly evaluate statistical quantities out of our solutions, and we inject all the results, maybe also you can put an arrow here, in an optimization tool that can be a shape optimization or in general a multi-objective optimization. So I would say that the challenge is not really to optimize each single block, but the challenge that we are asked to address is to make the whole process efficient and robust. So this is, in fact, what appears true is that the bottlenecks sits in the arrows at the moment. So most of the time in the product design, you get a big bottleneck when you try to let a computer-aided design system speak to a finite element solver and vice versa, because you have a loop here and you have to continuously exchange information from one software to the other. The use of splines and so of spline complexes comes into play when we try to construct a design through analysis tool, which means that we try to look at these two blocks together and try to optimize, to make them efficient and robust as a unique tool. So the idea of trying to make this effort of constructing this unique tool comes from Tom Hughes from University of Texas at Austin, who wrote, so together with co-authors, they wrote the first paper on a theory that is called isogeometric analysis. So this is the first attempt, and this is the first step forward into this direction, and they try to prove the interoperability between computer-aided design and PDEs. And they started from the very simple-minded idea. Let's look how objects are described in a computer-aided design system. Well, they are described by splines or generalizations of splines, like, for example, non-uniform rational B-splines. All you see here is represented is a spline representation of a technological object. And the naive idea is, okay, let's at least try to become compatible at the basic level. For example, we can do it by trying to solve PDEs using splines and NURBS as primitives instead of standard Lagrangian polynomials. So this is the beginning of a basically around 10 years research about this concept. And I think the interoperability between the systems is still far away, because a computer-aided design system is not a simple object. Does not produce simple geometries. It produces complicated stuff. It knows only surfaces and not volumes. The descriptions that one obtains suffer because of the tensor product structure. There are many reasons why this process is difficult to attain. But I think that the use of splines has been really a step forward in the construction of this tool, this unique tool from design through analysis. And there is also a lot of nowadays there is also a lot of attention that comes from the geometric modeling community, trying to talk and to get something in common in the middle. And I think that from my point of view as a numerical analyst of partial differential equations, the use of splines and NURBS turned out to be a powerful tool for the construction of numerical schemes for PDEs. And this is somehow part of what I want to talk about during my talk. So there is a very naive way to try to show why splines are good when I try to solve a differential problem. And this, I try to represent this in this picture. On the left, you have a standard Lagrangian finite elements. Well, no, Bernstein, by the way, finite elements. So here I have, so my domain is a segment divided into 3 pieces. These are finite element functions for p for degree equal to 1, 2, 3, and 4. And you see that I basically get p functions per element when I go up to degree p. And these are the splines of degree 1, 2, 3, and 4. Splines are piecewise polynomials of degree p and inter-element regularity p minus 1. So the splines are much less. I have much less functions that are sitting in my space. And what happens is that these two spaces, this one is much bigger than this one, have the same approximation capability, at least for moderate p. This tells me that I have the choice of solving a big system which is more sparse, or solving a much smaller system which is less sparse, but still it is much smaller. And so the idea that splines are actually effective because they exploit regularity to reduce the size of the system. Moreover, regularity is extremely beneficial in many applications, and this has been shown along the last 10 years with many numerical experiments. It is beneficial in applications like shells, where most of the time you have fourth order operator to solve. It is beneficial in contact mechanics because the normals are continuous and you do not suffer of non-existence when you try to project and to compute the gaps and so on. It is beneficial in computational fluid dynamics, and it is really beneficial in magnetohydrodynamics. So this is a very general motivation. Now I try to enter a little bit into my into the topic. So how can I use a spline to define a numerical method? And first I want to set my nomenclature so that it is clear once and for all. Here, what you see here is a parametric domain. The mesh that you see there is called so the points that you see here are the knot on the parametric domain. The functions that you see there are quadratic splines on that knot. Then if I have a combinations of these functions in the space, I get a computational domain. Here is the blue line is my computational domain. The red dots are called the control points. And what you see here, so the segments, the piecewise linear object, piecewise affine object that you see here is called control polygon or control mesh. This is what I would call all the time control mesh. So the mesh is not sitting in the computational domain. The control mesh is not sitting on the computational domain. And the one you see here is the not mesh. So I take these points and I map them through capital F on the domain, and this is the real computational mesh that I will call not mesh. Just because I will use this nomenclature all the time, I want this to be clear. So how can I construct a numerical method? So all is about constructing a finite dimensional space and then trying to use it within a Galerkin or a variational setting. So the idea is that I have a domain omega, which is this one, that is represented as a spline or a NURBS parametrization of a parametric space. Here I tensorize what I had in the previous slide. The general geometry we can treat at the moment is an unstructured collection of these kind of patches, and the discrete space is obtained by deconstructing splines in here and then changing the variable and getting splines over the physical domain. And the degrees of freedom are carried by the control mesh, which is the one you see there, while the computational mesh is the not mesh, which is the one you see here. And refinement can be obtained by not insertion and degree elevation. Here you see that I have refined the control mesh without changing the geometry. Okay, so the general geometry are multi-patch, can be structured like this, and with this kind of geometric structure, we can obtain actually already quite complicated and topologically non-trivial object. And I would say that this setting is quite a good setting for adaptivity, because we do not have a completely general mesh, but we have globally unstructured but locally structured meshes. And this is is a very good and nice setting for adaptivity. There is a lot of work that is done towards adaptivity in this world, and I would say that the two main keywords at the moment are T-splines, and there is a lot of activity about this. I just want to give a few names, and the other attempt is to use hierarchical splines within within the isogeometric context. So I think that now I'm ready to start with my spline complexes. So once it is accepted that I want to use a spline, I want to use a spline to solve my problems that had a relevant geometric structure. What can I do? Well, I start from finite elements. This is a very fast review on Whitney forms. So if I have a tet, I can define all these 4 spaces. These are the edge elements. So the pictures show the degrees of freedom, and this is the representation of the polynomial. These are the well-known Whitney forms, and it is known that if then I take a collection of tets and I take those as degrees of freedom and so on, I get an exact sequence as soon as the domain that I'm using is topologically trivial. So these are the standard P1, these are the edge elements, these are the phase or Ravier-Thomas elements, and these are the piecewise constant. So what are the main properties? And the reason why these elements are extensively used to solve many of the equations I showed before. The differential, there is a canonical choice of basis that makes the differential operators to be incidence matrices of the underlying mesh. So basically you just need to know the mesh and the connectivity of the mesh to construct all the operators you need. And the geometric structure is this one. So this complex is a co-chain complex of the underlying mesh. Everything is really, you can construct functions, you can be on the mesh only. Everything is, so the complex is the complex of the mesh itself. The same holds true when you have quad. These are called, well, this is the exact sequence that you obtain on quads, exactly as before. So you see that this part hasn't changed because it's exactly the same. I would say that these are called again Whitney forms, and the geometric structure is exactly the same. Now what I can do is that what I said before, if I want to make refinement, I can do not insertion and degree elevation. This is exactly what I'm doing. I take the unit cube and I do degree elevation and not insertion on the unit cube, and I obtain a sequence of spline spaces that are exactly obtained from these guys by raising the degree and raising the regularity together with the degree. So if I call S hat P1, P2, P3 the space of splines that are of degree P1 in the direction X, P2 in the direction Y, P3 in the direction Z, then I obtain, for example, S0 is this guy, because I start from this and I degree elevate. And then S1 is this, S2, S3. Again, as before, this sequence is exact, and actually it is exact because this is a cube, so the topology is trivial. So now I can do what I explained before. If I want to define the complex on my physical domain, I just have to make the change of variable. And this is we know very well how to do it in the differential geometry. So this is what I will do. If I take the space of functions or vectors that are in L2, such that a certain differential operator that I call D is in L2, then if my domain omega is obtained by the cube with the parametrization capital F, then I have that this, so let me read this piece by piece. So the second line is the sequence obtained by pullback the spline complex to the physical domain. And so you see that lambda 0 is just the pullback of the 1 forms in the parametric space. Lambda 1 is the pullback of the S1 and so on. So, and I have, by the definition, by the structure of the pullback, if the previous sequence was exact, this sequence is exact. And moreover, I have put projectors in that. I can project from the exact sequence on say Hilbert spaces. I can project onto my spline spaces with commuting projectors. And this is a theorem that we have proved maybe 2010 and published in 2011, that these projectors exist. And moreover, we can construct projectors so that they are L2 stable and they verify optimal error estimates, local optimal error estimates. So I just want to give some details about the consequences of having those projectors. So here I repeat again my theorem. The theorem is that I have L2 stable projectors that commutes and that verifies an error estimate. There are important consequences of this theorem, besides the fact that I can solve Laplace-like operators. There are other consequences that I try to explain here. So let me start again from the continuous setting. If I call K the image of the differential operators through of HD of omega, HD of omega can then be written as K plus K orthogonal, and it appears that for all orders of differential forms, K orthogonal is a subset of is a subspace of L2, of course, but it's also compact. It's compactly embedded in L2, and this is very important because it is related with the structure of a certain number of second-order operators, so starting from the Laplacian to the Hodge Laplacian. So depending on the order, you get a different type of operators, and the structure of the spectrum of those operators really is related to the fact that K orthogonal is L2, is compactly embedded in L2. Now, if we go discrete, I can take the discrete image, so the image of D when it applies to a discrete spline differential form, and again the space can then be written as KH plus KH orthogonal, and the main consequence of the theorem above is the following, is that the distance between KH orthogonal and KH is asymptotically small, in the sense that it goes to 0 when H goes to 0, and here I just reminded the definition of the distance between these two spaces. So this is the angle, if you want, between the two spaces is asymptotically small, and the main consequence of this is what is called the discrete compactness, and that has been introduced by Franco, by Daniele Boffi and other, and by also Kikuchi, for example. It has been by Kikuchi. And so in this paper, what I was trying to show is that this angle is really if and only if. So this angle is small if and only if the discrete compactness holds. And in fact, this is exactly a consequence of this theorem. The discrete compactness is the one that is responsible, for example, for the approximation of the spectrum. For all the second order operators I can solve with these spaces. And in fact, this is very much related to the stability of the discrete Hodge Laplacian and all the related PDEs. There is a nice paper, it's not a 2005 paper, but it is a 2008 paper, where really it is shown that once you have L2 stable commuting projectors, many consequences come, and here is just an example of the consequences. Okay, now I want to go back a little bit to the structure to see how the space I have defined actually can be constructed. So I have taken the standard Whitney forms and I have done degree elevation. This gives me a canonical set of spline bases, and it appears that with this canonical setting of bases, the operator matrices are again the incidence matrices of the underlying knot mesh. So again, for splines as for finite elements, everything is totally linked to the mesh. I just have to construct the incidence matrix of the mesh and I have the operators. The geometric structure is a bit more rich than in the case of finite elements, because the complex that I have here is isomorphic to the cochain complex of the knot mesh when P is odd, and it is isomorphic to the chain complex of the knot mesh when P is even. If you remember, in the case of finite elements, there was no possibility of constructing a chain complex, only so the Whitney forms are co-chain complex of the mesh. In my case, I have actually both structures. It depends if P is even or if P is odd. Now the degrees of freedom, and I have a second slide about this. We devoted some time trying to understand what are the degrees of freedom. It's because it is important when you speak, for example, I don't know, when you try to solve an electromagnetic problem, you want to know exactly what you're solving, what is the meaning of your degrees of freedom. Well, the degrees of freedom are basically the ones attached to low order Whitney forms on the control mesh. And I will try to explain this a little bit, because I think it's a part of the interest. It's a part of what we are doing. So here is a way to explain this concept. So if I take G0, G1, G2, G3, be the low order Whitney forms attached to the control mesh. Given a domain, I have a control mesh, which is now a piecewise cubic mesh, and I can construct the Whitney forms on that cubic mesh. Then I can take these, so this is the exact sequence of Whitney forms, and this diagram commutes where I, all the operators I that you see here, are the identification. So I take, given a control field, for example in here, I take the coefficient of this control field and I attach it to the spline, and vice versa. So I identify splines and Whitney forms by identification of the coefficients. If I do so, I get a diagram that commutes like this, and this means that the degrees of freedom that are the same on top and on bottom are exactly the degrees of freedom of the low order Whitney forms on the control mesh. So this is an example. This is the positions of the degrees of freedom, for example, for this guy. Colors does not match, but the picture was too hard to replace. Okay, so these are the degrees of freedom of the zero forms, and these are the degrees of freedom of the one form, for example. So fluxes, well, circulations along edges of the control mesh. And there is a remark that is due here. So basically what I'm saying is that I have, in my spline complex, I exactly have the structure of low order Whitney forms. So what's the point in constructing splines, I can ask myself. So I have exactly the same geometric structure. Well, the point is that, so these two complexes are completely isomorphic, they have the same degrees of freedom and so on, but the complex on top, which is the one of splines, actually deliver approximations of order p. Because p is fixed, when I take a certain p, then I deliver approximation of order p, while the underlying Whitney forms deliver only approximation of order 1. So as soon as it is possible, it is much better to use the spline complex while having the same structure as Whitney forms. Okay, now I have, yes, I think I'm perfect. So what happens in the multi-patch, again, I can use all what I know, so I can glue different patches just gluing the Whitney forms before. So I can construct the Whitney forms on a general mesh, and I just have to glue the degrees of freedom. So when the two edges are, I decide that they have to be together, I identify the degree of freedom. And here I do exactly, so if I do this, so if I identify degrees of freedom, then I get a complete gluing, so I get the definition of the spline in the multi-patch structure. Okay, so this is what I wanted to say about the construction and the properties of the complex. And now I go to the star Hodge operator. And I have 10 minutes left, right? Yeah. All right, okay. So, just very briefly, what is the star Hodge operator? It's a canonical isomorphisms that maps, forms of order I into forms of order d minus I, where d is the dimension, in my case is 3, so I wrote just 3. And is defined like this, where the dot is the scalar product on alternating forms, and the omega is the volume form. Why am I interested in this operator? I'm interested in this operator because the Hodge operator is the one that represents constitutive laws in basically all the equations I have shown before. So if you want to model in terms of geometric quantities constitutive laws, you naturally get into Hodge operators. So from the numerical point of view, a correct discretization of an Hodge operator is related to a compatible representation of constitutive laws that can be very interesting in a certain number of problems. In the case of finite elements, there is an extensive use of construction of star Hodge operators, especially in computational electromagnetics, which is a very tough problem to solve. But unfortunately, it calls upon the construction of dual meshes. The construction of dual meshes is not always a simple task, and especially in 3D, is not very easy. But this is what is done for in computational electromagnetics by a number of teams and software. So what can we do in the case of splines? Do we have any good news? I think there is a good news, and is the following. So if you take the spline complex that you have here on top, and then I define another one. It's the same complex, but defined on the degree p minus 1. So I have a complex which is based on degree p, which means that the first space is of degree p, and here I have another complex which is based on degree p minus 1. So the first space is made of splines of degree p minus 1 in all directions. Here is an example, for example. So the lambda 1 of this guy is this, and the lambda 2 of this guy is this, for example. And I need one of the two to be endowed with natural boundary conditions. So otherwise, normally the Hodge operators works on a closed surface. But anyway, so this is just a detail. So if you make this choice, then there is a canonical construction of a spline star Hodge operator that is constructed like this. So I have an operator that goes from a spline of order I to splines of order 3 minus I, but with the tilde. And this is an isomorphism which is uniformly stable in L2. it converges to the star Hodge operators in operator norms when h tends to 0. And so this is the definition. It's just somehow it's the L2 projection of one function onto the other. And it appears that yes, that it is uniformly stable. If you look at here, what it is written, here I have a mass matrix, and here I have a grammar matrix. So when I say that the operator is an isomorphism, I mean, this means that the mass matrix is uniformly invertible, which is of course true, but also that the grammar matrix is uniformly non-singular, which is not easy to prove, which is a statement to prove, say. And the fact that it is uniformly stable, it means that the grammar matrix is uniformly non-singular, and this is why it works. The operator is not sparse in general if you define it like this, because here I have an inversion of a mass matrix, which gives me a non-sparse operator, but maybe sparse constructions are possible and they should be investigated further. So I think that I'm now at my conclusions, and so I have defined spline complexes. They can be used in many different contexts, and the existence of an easy to construct star Hodge operators is a plus in this field, and I think it deserves further attention. I think we can make something out of this. And here is a list of applications that has already been investigated and tested extensively. So the first, so in electromagnetics, there has been a lot of work in eigenvalue computations, in waveguides analysis, and in integral equations. There is a lot of work to do in integral equations. I think it's really a nice subject to explore. In fluid dynamics, John Evans and co-authors has defined fully divergence-free approximation of fluid velocities, and they have also used these spaces to discretize Darcy-Navier-Stokes coupling in a very straightforward way. And in solid mechanics, it has been used to approximate a thin plate, and also in the context of collocation methods. So I think this is more or less all what I wanted to say. No, there is also a last slide, I'm sorry, I forgot. Yes, I was, because I had the wrong number. So the last thing I want to say is that we have two libraries that are now available to public if you want to try your favorite equations with splines. The first library is a MATLAB library that is called the GeoPDs, and you can download from this web page. And we also have, a beta version of a C++ library that is called IGATools, and is available as a Google code on this site, on this website. And in both cases, you find the basic constructions that you need then to program yourself the equations you may be interested in. And in both cases, you can also solve equations over surfaces, for example, which may be interesting. Okay, the final thing I wanted to say is that a survey paper is available now on Acta Numerica 2014, where basically most of the results I have presented here are written, and also where a lot of numerical tests are presented in many different contexts. So I would like to thank you for the attention. Thank you very much.
Okay, thank you very much for a very interesting talk. So we have enough time for discussions. So anybody has questions or comments? Please.
I have one question. So if I have understood, everything is tuned toward hexahedron cubes?
Yes, cubes.
So what about other geometries, tetrahedrons?
I don't think tetrahedra is an option here, because defining splines over tetrahedra is difficult. So there are there is, I don't know, maybe 20 years of research about how to define splines over tetrahedra. And it's just a very difficult topic. I'm not sure. So there are constructions, but the problem is that they are so difficult that you may not be willing to use them then to compute, to use as to solve a partial differential equation. So I don't see an easy way to construct piecewise polynomials that has a certain high continuity across vertices, edges, and faces on a general polyhedral, on a general tetrahedral mesh. So I think here the framework is that I have a locally structured, a globally unstructured mesh, and it can be that I have local features that can be described with adaptive refinements or with a priori refinement in a non-tensor product fashion, but I would say that I cannot really treat tetrahedra.
Okay, any other question or comments? I don't see this side, so nobody there. So any questions? So if not, maybe let me ask you a question. So in adaptivity, you are allowing just one hanging node for like a T-junction, or you allow more general case? I mean, for the, you mentioned about adaptivity.
One can allow a very general non-tensor product structures. There are conditions. It's difficult, by the way. The screen is gone, but but I think I had I think I had no pictures on the screen. If I do like this, I go to the beginning. No, I don't remember if I had some pictures. No, I had no.
You had to just stated T-junction, T-spline, so that's where adaptivity may come in.
Yes.
There.
So in the case of hierarchical splines, you have to think that you can really add on top of a spline tensor product mesh, you can add patches, refined patches in a very hierarchical way. And what you can show in theory and then also in practice, that you preserve stability even when you do very weird hierarchical structure for splines. In the case of T-splines, there is a lot of literature showing exactly which kind of T-junctions are allowed, which kinds are not. It's very general what you obtain. The problem is the refinement process, is whether you can actually preserve the properties that you need within refinement processes.
So in terms of this adaptivity, do you have also any work having like reliability estimate for your problem so that it's totally under control, like a residual base or?
In the case of T-splines, no, and I don't think it's easy to do.
Okay.
In the case of hierarchical splines, we have studied the convergence of adaptive techniques. So together with Carlotta Giannelli, there will be soon, I hope, a series of papers where we study reliability and efficiency when we use hierarchical splines, and we actually prove optimality. So we can
so you proved the convergence of adaptive iteration.
Exactly. So we can prove convergence of and optimality of adaptive iterations.
Okay, good. Okay. So then, any other question or comment? Okay, there, Eric.
Can your approach be extended to non-Euclidean Riemannian matrix?
I don't know. Maybe, yes, maybe, but I don't know.
Any other question or comments? So, because I can still, yes, maybe let me ask you one more. So I think this.
Don't feel obliged.
I'm curious. So this approach seems to be very promising, but can you tell people that if somebody is interested in this approach, what problems are left? I guess pretty much well developed, but there are still some problems. So can you mention some of the open problems or any good problems to start or anything in this approach?
So it depends. No, this really depends. I mean, it's not true that that a lot of things has been done. On the contrary, I would say that there are mainly open problems in the sense that I don't know, when you, for example, just to mention examples, let me go back to to my problems here. Where are they? Okay, so these problems, exterior domain problems. This is a very promising technique because I do not need the mesh in the volume. And here I can really take an output from a computer-aided design system because I have the description of the surface, and I can try to keep the description of the surface that comes from the geometric modeler and try to run then an exterior domain problem. Now the question is, how can I construct an efficient integral equation solver? Because my basis functions are splines, and I can ask myself whether if this will affect, for example, the behavior of a multiple expansion in this context. So all this has to be explored. There are, I don't know, maybe 2 or 3 papers about the use of splines in the case of integral equations, but they are not very exhaustive. So it's a complete new field to explore, and it's only about acoustics and not electromagnetics, for example. And I think that also, we have heard even this morning, all the equations on surfaces and the nonlinear, so for example the Wilmore flow that we have, that the plenary speaker today discussed about, that these are equations that that are very suited to this kind of approach, because the surface moves and has to be regular, because the flow that you are approximating actually involves the curvature, and the curvature is the Laplacian of something, and you have a fourth order operator, a nonlinear fourth order operator over a surface, and I think this is an interesting topic for which the use of splines is very much suited. And I don't think that there exists no theory and there exists no practice in that. There are many problems where there exists a lot of practice, but no theory, because it's an approach that is taken mostly by engineers at the moment.
Okay, so let's thank Annalisa Buffa for a very interesting and stimulating. Okay, then we have a break, 15-minute breaks, and
Oh, yeah.
sorry. So I forgot, this is my first time to be a chair, so
Okay, thank you.
right from the